Okay.
Welcome, everybody, to PALS. Today, Ronnie Thornton is going to talk about CSP in descriptive set theory. He's ready.
Yeah. Thank you very much for having me. I'm usually talking to audiences who know a lot about descriptive set theory and not so much about constraint satisfaction problems. So it's nice to maybe have something of the reverse happen. Um, and some of you might have seen Zoltan Vinyatski's talk a couple of weeks ago, which is very nice, gave a good overview. If you haven't, don't worry. I'm not going to assume, I barely remember what happened 2 weeks ago. I'm going to start by trying to give a little bit more context for these kinds of problems that we study. And then I'll indicate some of the difficulties in adapting some of the classical tools for setting CSPs to this new context. And then I'll end maybe with some questions that I think some algebraic insight might be useful for. Okay, so uh, I work in descriptive set theory and more narrowly in an area called descriptive combinatorics, where we study sort of definable instances of combinatorial problems. Um, so what do these words mean? Um, so first off, combinatorial problems, very broadly, uh, we have some sort of structure, typically relational structure, maybe something like a group action, and we want to decorate it or find some sort of map out of the structure. So for instance, we're interested in things like graph coloring, or more generally, we have some structure X and some target D in the same signature, and we want to know if there's a homomorphism from X to D. And I'll use this arrow notion to mean that there's a homomorphism from X to D. Or maybe we're interested in something like counting orbits of some group action, or maybe something like finding anti-chains in a poset. Uh, we could go on all day listing problems. And then definable means that these structures we're working with, the graphs, the relational structures, the group actions, they all live on some kind of space, topological space or a standard probability space, or these sort of slightly more exotic things like standard Borel spaces. And we want our solutions to be definable in the sense that we're avoiding the axiom of choice. We want uh, our solutions to be presented in some nice way, and this often ends up being equivalent to saying that they exhibit nice geometric properties. So, for instance, we could look for continuous graph colorings. We have a graph on a topological space. We want a continuous function on the space that sends neighbors to different points. Um, and so continuous, this plays nicely with the topological structure. It has nice geometric properties. It also has a nice concrete presentation. We want to know finitely many bits of the output. We only need to know finitely many bits of the input. We can code this all in various nice ways. There are more relaxed notions like Borel, which is sort of closing up continuous things under countable operations. Um, um, Maybe if we have some measure mu, a Borel measure, on some nice space, we might look for mu measurable solutions, where we have a Borel code for a solution that works very well, except maybe on some negligible small set that we don't care about, some measure zero set. Or perhaps even more exotically, we might want solutions in Elevar, which if you're not familiar, don't worry too much, but this is like the smallest model of set theory without choice that contains all the reals. So anything that you can build in a set theoretic way out of real numbers, that's what Elevar represents. So those are different definability notions. And again, I could go on. That's sort of the general flavor of problem I work on. And a classic example that Zoltan mentioned, so let me clean up some of this stuff, is this irrational rotation graph, right? So um, uh, we pick some angle theta that is, an irrational degree, and we connect 2 points on the circle if they differ by an angle of theta. So classically, this is a two regular acyclic graph, right? Because theta is irrational, you're never going to get back to where you started, so it's acyclic, and everything has two neighbors. Um, and so classically, we can two-color it, right? We can pick a point in each component and then alternate colors from that point. And also classically, it has continuum many components, right? There are continuum many points on the circle, and each component is countable. It's just a copy of Z. And so there have to be continuum many components. But in this sort of definable way of thinking about things, there's not going to be a measurable two coloring, essentially because of ergodic theory. Uh, so I don't want to get too lost in the details of this proof, but roughly, measure theory tells us that any measurable set is going to look a lot like an open set. And then because orbits are dense under an irrational rotation, if you start translating an open set around by 2 theta, you're going to eventually uh, cover the whole graph. So if you start moving around inside of one color class, you're going to hit another color. It's a sort of contradiction. Right, and so not measurable, so certainly not going to be any Borel coloring. In fact, under mild large cone hypothesis, uh, no coloring in L of R. And also in L of R, again, you need to assume some large cardinals, but won't go into too many details. There's no injection from the components into R. Right? So there's no definable way of numbering the components with real numbers. And what's sort of underlying the combinatorics of this is that there's no definable way of picking a point from each orbit, right? So to two color, we had to pick a point in each orbit and then two color from there. But there's no way, we're avoiding the axiom of choice. There's no way of making that choice definably. Other way of sort of parsing this out is saying that if we look at this quotient, if we try to collapse all of the components down to points, uh, then this quotient, right, is really nasty. If you think about actually what the quotient of the circle could possibly look like, it's really difficult to try to understand. And in particular, there's no definable way to put a standard Borel structure on it. There's no complete separable metric you can put on the quotient in a definable way. Okay, so a sort of general lesson here that will come up again is that quotients are bad. Okay. And feel like I should mention this just because it's interesting and it's an important background, but I won't go into too much detail. There are formal connections between this area, Borel and measurable graph labeling problems, and problems in distributed computing and problems about graph limits. Right? This is taking this sort of zoomed out view. This should make some sense, right? If you're doing distributed computing, you don't want to pick one processor to do all the work for you. There's no distributed way of selecting out a nice point from an entire network. Um, and also in this distributed setting, quotient's gonna mess up all your problems. If you're trying to measure how much communication happens across a network, you don't want to think about collapsing the network down to a point. Okay. Um, Good. So they're the kinds of problems that I think about this one particular example that is nice and illustrative and some interesting connections with other areas of math. Drink some water. So what kind of theorems are we interested in this area? In the Borel and L of R context in particular, we're interested in these so-called, oh gosh, uh, dichotomy theorems. And um, you might have heard about the CSP dichotomy theorem before, and that's different kind of dichotomy. So like separate that out in your mind. There are lots of words that sound very similar in these areas, so we have to be careful. So what do I mean by dichotomy? Well, first let's look at an example. is a very beautiful theorem of Silver that says that if we have a Borel equivalence relation, say on the reals, could be any polar space, but let's work on the reals for now. Either its quotient is countable, and in fact, there's a Borel witness to this fact. There's a Borel map on R that is constant on equivalence classes that takes Hamiltonian values. Or uh, there is this canonical obstruction. There is a Borel way of taking the reals and sending different points to different equivalence classes. Okay, so this right-hand fork we can think of as saying that uh, the reals injects into the quotient definably. And some notation that you might want later on. Um, so for Borel equivalence relations, I guess equivalence relations more generally, E and F, we said that E Borel reduces to F if there is a homomorphism simultaneously from E and its negation to F and its negation. So there's a Borel map that sends E-related points to F-related points and sends different E classes to different F classes. So this is, we're generally saying that it's a definable witness to the quotient by E injecting into the quotient by F. And so this right-hand fork of Silver's dichotomy is saying that equality on the reals, Borel reduces to E. Okay. Um, and then there's some machinery we can crank. There's some general techniques of taking a Borel dichotomy like Silver's and getting some nice results in L of R. So a result that I believe is due to Hjort set in L of R, we have an equivalence relation. Its quotient will be either well orderable or the reals will inject into the quotient. Right? So in particular, if we have an uncountable set in L of R, then either it contains a copy of the reals or it contains a copy of omega 1. Right? This is, I think, a very nice theorem. If you're of a certain philosophical bent, you might think of this as in some ways resolving the continuum hypothesis, right? Uh, the continuum hypothesis asks, is R the same as omega 1? And the answer is no, but there's nothing else. There are only two witnesses, definable witnesses to uncountability. Um, yeah, uh, okay. But if you're not, so inclined philosophically, you might also like to know that this theorem and its relatives have nice applications to operator algebras and ergodic theory and model theory. This gets you like most of the way to the thought conjecture. Okay. Um, More generally, a dichotomy theorem for some problem tells you if you have a Borel instance of the problem, either you have a Borel solution, or there is some reason why, some canonical reason why. There is some uh, Borel homomorphism from some canonical structure Y into X that prevents you from having a solution. Or maybe there's not one canonical obstruction, maybe there's like a small family of them, but typically there's just one. So some examples. Um, there's theorem of Kekres, Seletsky, and Todorcevich that characterizes when do you have a Borel homomorphism from a Borel graph into the complete graph on the naturals. So when is there a Borel countable coloring of your graph? And it's exactly when there's no homomorphism from some crazy graph they build called G0 into G. The G0, uh, one way to think of it is as the projective limit of a generic sequence of trees. Um, Similar theorem of Karawa, Miller, Sritesser, and Vidyatsky characterizes when there's a Borel 2 coloring of the graph. And here there's a canonical obstruction. Either you have a Borel 2 coloring or there's a Borel homomorphism from something called L0, which is a projective limit of a generic sequence of lines. And then some more problems about equivalence relations. Theorem of Harrington, Kekres, and Louveau characterizes when you have a Borel reduction to equality on the reals. When you have a Borel way of injecting from the quotient by E into the reals. And The instruction there is this funky equivalence relation called E0, which there are lots of ways of presenting E0. One of them is, in fact, that the equivalence, the protectiveness relation for the rational rotation graph. This is the minimal counterexample. So there are lots of nice dichotomy theorems. They tell us that various problems in the Borel setting and the L of R instruction setting, they have lots and lots of structure. They have lots of applications in various areas. And as logicians, whenever we see lots of nice stuff happening, we often think to ourselves, can we ruin everyone's good time and say that a result is impossible? So how might we prove that there's no dichotomy theorem? One way to do this is with complexity. Um, so the relevant measure of complexity here is something called projective complexity. This is a quantifier counting complexity, where we count quantifiers over the reals or over continuous spaces. So a set S, which you could think of as a set of reals or of codes for objects that you can code with reals, is sigma 1, 2, if you can write it as an existential quantifier followed by a universal quantifier over some Borel condition. And it says pi 1, 2 if it's the complement of a sigma 1, 2 set. So if it's equivalently a universal followed by an existential quantifier over a Borel condition. Those some examples. Asking whether or not there is a Borel homomorphism between two structures is always a sigma 1, 2 problem. And you can write this as there exists a Borel map. Okay, there's something funky about coding Borel maps with reals, but it's a technical point that I don't want to get too bogged down in. So that every tuple that's rated in X gets sent to something that's rated in Y. So this is a universal, sorry, an existential followed by a universal, followed by a simple impact Borel condition. Okay. In particular, anytime we have a dichotomy for a problem, right, this says that phi is a dichotomy, then satisfying phi means that you don't have this canonical obstruction homomorphing into you. So it means that satisfying positive side is equivalent to saying negation of a homomorphism problem, and so you're pi 1, 2. If you have a dichotomy, then your negation is equivalent to a homomorphism problem, so your negation sigma 1, 2, so you're pi 1, 2. In particular, there's a classical theorem, maybe you could attribute it to Luzin, that says that there is some sigma 1, 2 set that's not pi 1, 2. It's a diagonalization argument. You take a universal sigma 1, 2 set, it'll work. And so if you have a really complicated problem phi, say a problem that's complicated enough to have a reduction from any sigma 1, 2 problem, from any homomorphism problem, for instance, then phi has no dichotomy, right? It'll be strictly sigma 1, 2. It can't be pi 1, 2, and so it can't have a dichotomy. And major example of this is Borel graph 3 coloring is sigma 1, 2 complete. That's a theorem of Todorcevich and Vidyatsky. So no dichotomy for 3 coloring. The 3 coloring problem for Borel graphs has no real structure to it in full generality. Questions so far? Okay. So shortly after Todorcevich and Vidyatsky published their paper, I believe Marx and Kekris asked at a workshop for Ames, for which G is this graph homomorphism problem sigma 1, 2 complete. And you can ask a similar question. I don't think Marx and Kekris knew much about the CSP stuff when they asked this question, but naturally generalizes. What about a Borel version of the CSP problem for a fixed template in general? Which I'll go into more detail exactly what I mean by that, but I'm sure some of you already have an idea. Okay. So that's some background on the descriptive set theory side. So now I want to maybe remind you a little bit about some of the classic theory of CSPs in the finite setting, homomorphism problems, and some of the algebraic tools that get used to solve it. So first, let's recall this polymorphism PP definition duality. Um, this is the mathematical sense of the word recall, where maybe I'm telling you this for the first time. So we have a relational structure D. A polymorphism of D is some homomorphism from a power of D to D. Right? So here the power of D, so we're on the same page, this is the categorical power, where we relate a bunch of tuples if the relation from D holds at each coordinate of the tuples. Okay. Um, so in particular, if I say hand you a list of n homomorphisms from some structure into D, by composing those n different homomorphisms into D with a polymorphism, I get just a homomorphism into D. Um, and the polymorphism algebra for D, which I'll write Pol D, is just the set of all of these polymorphisms. It's the union over n of all of the homomorphisms from D to the n into D. Those n needs to be finite here. It turns out that this algebra of polymorphisms under containment is dual to a syntactic relation between uh, uh, relational structures. So for a relation R on a set X and some structure D also on X, so everything has to be on the same domain for now, we say that R is PP definable in D if we can write R as uh, an existential quantifier, maybe some dummy variables, in front of a big conjunction of atomic formulas, right? Where atomic formulas are allowed to include equality. Point I will emphasize because it comes up later. Right? So this sort of picture here, right? We have our relation R, maybe it's some ternary relation, and if R can be PP defined in a structure D, we can replace every instance of R with some constellation of relations among some relations that come from D, maybe some equations, and maybe we need to also add in some dummy variables. Okay. So PP definability says that we can replace R anytime we see it with some constellation of stuff that comes from D. Um, and it should be not too hard to see. Maybe it takes a minute to think through carefully, but surely it should be at least believable that if we have a polymorphism for D, there will also be a polymorphism of anything that you can PP define in D. Okay. So we can extend this relation between a structure and a relation to a relation between two structures. Right? If we have E, some structure that also lives on X, right, has the same domain as D, we say E is PP definable in D, which I'll write with less than subdefinable, to mean that just all of the relations in E are PP definable in D. If we want to compare structures on possibly different domains, there's a notion of interpretability, which is just the usual model theoretic notion of interpretability, but all of the interpreting machinery has to be PP definable. So E is PP definable in D, which we write with less than subinterpretable, if there is some power of D and some uh, subset of the power that's PP definable and some PP definable relations on the subset and a PP definable equivalence relation. So that if we quotient out the subset with the relations by the equivalence relation, we get a copy of E. Okay, so E is some PP definable quotient of something definable in a power of D. And theorem is that these notions of polymorphism and PP definability and PP interpretability are in a Galois correspondence. So a structure E is definable in D exactly when all of the polymorphisms of D are also polymorphisms of E. Okay. So the left to right direction, not too hard to think through. The right to left direction takes some clever ways of building interesting of building interesting relations, just knowing about the polymorphism. And then for interpretability, it's not enough to know that uh, the polymorphism algebra for D is a reduct of polymorphism algebra for E. Uh, but what you need is that polymorphism algebra for D has some reduct that's in the variety generated by the polymorphism algebra for D, in the HSP, the polymorphism algebra for D. So another way of saying that is you can interpret E and D if any uh, if any algebraic equations satisfied by polymorphisms of E are also satisfied. Sorry, let me make sure I have this right. Any algebraic relations satisfied by polymorphisms of D are also satisfied by polymorphisms of E. And this duality has seen a lot of applications in like computer science and finite combinatorics because PP definability is one way to formalize the notion of a gadget reduction between homomorphism problems. So in the finite setting in computer science, here's one way this shows up, one precise way that this shows up. So first, CSP for D, this is just the problem of deciding for a given structure X with the same signature as D, does it have a homomorphism to D? And a theorem is that if E is PP definable in D, or interpretable, then the CSP for E polynomial time reduces to the CSP for D. And I'll sketch a proof of this. For definability, the proof for interpretability is the same. You just have to keep track of more indices. Right. So let's say that we have an instance of our problem E, right? Maybe E was that triangle relation from before. PP definability says that anytime we have a triangle, we can equivalently replace it with some constellation of relations from D. And picture I drew looks something like this, possibly including equality. Okay. And so the picture on the left will have a homomorphism into E, if and only if the picture on the right has a homomorphism into D that sends, things where I've drawn an equal sign to the same point. And this map that takes a triangle and replaces it with a bunch of lines, that's really easy to compute. I can certainly compute it in polynomial time, like linear in the number of relations. Okay. What I've drawn here isn't quite an instance of D, it's an instance of D expanded by the equality relation. So then I have to take a quotient, which is no problem in the finite setting. Okay. So that's, proof by picture. And so you can start classifying CSPs up to polynomial time equivalence using some algebra. So as a simple corollary of this proposition of this proof I just sketched, if the variety generated by the polymorphism algebra for D contains a non-trivial projection algebra, then the CSP for D is NP complete, right? If the variety generated by the algebra for D contains a projection algebra, that means that, for instance, 3-sat. So polymorphism algebra for 3-sat is just a projection algebra. So 3-sat can be interpreted in D. Everyone knows 3-sat is NP complete, and so the CSP for D is also NP complete. And the theorem of Bulatov and Zhuk independently says that essentially the converse is true. There are some technical conditions you need to assume. Don't want to get too bogged down in the details. Essentially, we need that D has every singleton unary relation as a predicate. And you can always reduce to that case by doing some annoying little manipulations. But under these mild technical assumptions, uh, if we have some structure whose polymorphism algebra does not have a projection algebra in its variety, then that CSP is polynomial time solvable. Okay. So in particular, if P is not equal to NP, then having an NP complete CSP is exactly the same as having a non-trivial projection algebra in your HSP, up to passing to a core and expanding by unary relations. That's a brief sketch of the algebraic approach to CSPs. So any questions so far? Okay. I'm sure that you all know this material much better than I do, but brief sketch of it. All right. So can we use these ideas to settle complexity questions in the Borel context? And the answer is kind of. So this first step, where we take a relation that's PP definable in D and replace it by some constellation of relations and equalities, that's perfectly fine. We can do all that in a Borel way. But the second step, we have to take a quotient. And if you recall, quotients are bad. We can't take quotients in the Borel setting. The general, if you take a quotient of a Borel structure by a Borel equivalence relation, what you end up with, you can't put any Borel structure on. Okay. So what can we do? Well, we can expand all of our structures by equality, and everything lifts just the same and everything works out and you get some nice theorems, but then you're asking different questions. You're asking about satisfiability of constraints where you are always allowed to use equality. And often when you're doing set theory, you really are interested in graph coloring, say, not graph coloring that also is invariant along an equivalence relation. So the other thing we can do is we can weaken our notion of reduction or definability. So um, uh, the simplest thing you can do, which I will call a simple definition, is the exact same as a PP definition, but you're not allowed to use equality. So we say that a structure D simply defines a relation R if R can be written as an existential quantifier over a conjunction of atomic relations in D, not including equality. So no equality. It's not something I generally demand, but in this case, it's important. And then the relations for structures are completely analogous to the PP relations. Just we're never allowed to use equality. And simple proposition, which is just drawing that picture I drew earlier again, but without the quotient step, is that if E can be simply interpreted in D, and the CSP, the Borel CSP for E is sigma 1, 2 complete, then the Borel CSP for D is also sigma 1, 2 complete. Complexity passes upward through simple interpretation in the Borel setting. Okay. So if we want to start using some of the algebraic tools to understand complexity in the Borel setting, we need to see to what extent can we talk about simple definability using these algebraic tools. And there's one nice theorem along these lines, which amounts to staring at the proof of the classic Galois correspondence and seeing when you actually need equality. This theorem says that, okay, it's a bit technical, but if a reduct of the polymorphism algebra for E is in HS of our polymorphism algebra, not HSP, but just HS, homomorphic image of a subalgebra. And we have this technical condition that no relation in E projects onto the equality in any two variables. So none of the relations in E imply any equations. Then E is simply interpretable in D. Right. So for example, 3-sat, you can write it in a nice way so that no relation generating 3-sat implies an equation. Also for For instance, for structures that code graph coloring problems or structures that code systems of linear equations, they can all be massaged in this setting where we don't imply any equations between two variables. Um, and then, the question of understanding interpretability of these structures boils down to understanding what is our polymorphism algebra in the HS, the larger algebra. Um, and in the case of projection algebras, that's not so bad. In fact, if the variety generated by G contains a non-trivial projection algebra, then already HS, the polymorphism algebra for D, contains a projection algebra. Um, uh, this is like mentioned in a technical note of Bulatov somewhere, but I also give a proof of it in my paper on this stuff. Um, and as a corollary, if we have a CSP, so if we have a structure D that is NP complete, CSP is NP complete. So from Bulatov and Zhuk's theorem, assuming P is not equal to NP, D has to include a projection algebra in its HSP. From this lemma, that means it includes a projection algebra in its HS. So from the theorem, that means that D simply interprets 3-sat, and it follows from Dorshevich and Vinyavsky's work that 3-sat, Borel 3-sat, is sigma 1-2 complete. So the Borel CSP for D is also sigma 1-2 complete. Okay. So long story short, if we have something that's complicated in the finite world, it's also complicated in the Borel world. The reason why is that being complicated in the finite world, not only is it witnessed by PP interpreting everything, it's witnessed by, in fact, simply interpreting everything because of this nice algebraic fact about varieties that contain projection algebras. Okay. So as a corollary, we can answer Marx and Kekris's question. I have to say a few more words to get rid of this P not equal to NP business, but it's just making precise some of the algebra involved. For a finite graph G, the Borel homomorphism problem with template G is sigma 1-2 complete exactly when G is not bipartite. When G is bipartite, this homomorphism problem is the same as two coloring, which we know has a dichotomy from Kerwa, Miller, and Vinyavsky and Schrittesser. Okay, let's see. So that was a quick explanation of how some of this algebraic machinery can give us some nice negative results, or if you prefer to think of it this way, as proving some complexity results. There are, plenty of open problems left and some conjectures that I'll state later. But since I have a little bit of time, maybe let me also quickly sketch one. Sorry. Let me quickly also sketch one positive application of this theory. So again, in this technical sense of recall, where maybe you're learning this for the first time, there is a nice algebraic characterization of when arc consistency, or if you prefer to think of it this way, unary propagation, constraint propagation is enough to solve the CSP for a structure. Okay, so the definitions I'm going to give are like equivalent to all the definitions that you might see in the literature, but maybe slightly anachronistic. Maybe there's a definition you would prefer to take as fundamental, but exercise to check that it's the same. So by with one structure, what I mean is structure where there's a homomorphism from this funny P of D structure. We build out a D. So it's a homomorphism from P of D to D, where P of D is this structure whose domain is a collection of non-empty subsets of D. And we put a relation among a tuple of sets if every element of each of the set can be extended to a tuple by choosing elements from the other set that satisfies our relation. Okay, that's a mouthful, but here's a example. If we look at the complete graph on two elements, 0 and 1 are related to each other, non-empty subsets, 0 and 1 and 0, 1. Okay, so we want to know which pairs of sets can we extend any element of each of the set to an edge by choosing an element from the other set. Okay, so 0, we can expand any element of 0 to an edge by choosing an element of 1, but we cannot expand any element of 0, 1 to an edge that includes 0, because we can't pair 0 with 0. But there is a self loop at 0, 1. We can expand 0 to an edge, so we can expand 0 to an edge with 1 and 1 to an edge with 0. Um, okay. And uh, D is with 1 if D has a homomorphism to P of D. This is P of K2. So in this case, there is no homomorphism from P of K2 to K2. So K2 is not with 1. Though there are, of course, examples of structures like this. So something like Hornsat, which is satisfiability for Horn sentences, things of the form x1 or x2, and x2, and xn implies y. Sentences of that form, satisfiability for sentences of that form, that does that is with 1, have with 1. Okay. Arc consistency, so for x, an instance of D, we say that it's arc consistent if there is a homomorphism from x to P of D. So there's some way of assigning non-empty sets to every, so think of these as sets of possible values to every variable in x, and it's arc consistent if anytime we have a possible value for some variable and some relation that contains that variable, we can extend this possible value by filling in possible values for the other variables in that relation. Okay. So arc consistency is a necessary condition for satisfiability. The question is it sufficient? And sufficient if and only if, of course, P of D has a homomorphism to D. So a theorem is that if we have a Borel instance of D, which is arc consistent, meaning that there's just a set theoretic homomorphism from X to P of D, you can build it however you like using the axiom of choice, then in fact there is a Borel instance. And the reason why is, very briefly, if you want to build a homomorphism into P of D, you start by giving every vertex all options for its possible value, all of D, and then iteratively tossing out any variable that fails to extend. And anytime you can build an object by a nice canonical process of thinning out like this, you can do it in a Borel way using a technical tool called the reflection theorem. So this is a fairly easy theorem, but it has a nice corollary that if you have a width 1 structure and a Borel instance that has a polymorphism to D, that has a homomorphism to D, then in fact X has a Borel homomorphism to D. So for width 1 structures, sort of the CSP and the Borel CSP are like identical, right? These are like essentially classical structures. Adding Borel doesn't change your life at all. Turns out that the converse is also true. In fact, there's quite a lot of things that turn out to be equivalent. So I've written down 5 here, but I could spend all day adding to this list. So the following are equivalent, as D is width 1, that having a Borel homomorphism to D is the same thing as having just a classical homomorphism to D for Borel structures. If you also have some measure floating around, having a Borel homomorphism to D after throwing away a null set, so having a measurable homomorphism, the same thing as having a homomorphism to D, right? So if D is not with 1, we can find some structure that has a homomorphism to D but has no measurable homomorphism. Is equivalent to this sort of asymptotic satisfiability statement. So if we have a sequence of structures that have uniformly bounded degree, so every vertex is involved in at most D relations for some D, then having it so that for every radius, the probability the ball of radius R around a vertex sees some abstraction to homomorphing into D, as long as that doesn't happen mathematically. So the probability that you see no obstruction within radius r of a random point, if that goes to 1, then in fact you can find a sequence of functions that asymptotically satisfy a proportion of constraints that tends to 1. Okay, so this first line says something like asymptotically constraints disappear locally, and the second one says that asymptotically we can globally solve the problem. Okay, and it turns out that that happens if and only if your structure is width 1. This is also equivalent to saying that ZF without choice can prove a version of the compactness theorem for your structure. Um, I can sort of go on. And maybe one interesting fact is that this implication from 3 to 4 is automatic. This follows from some nice results about graph limits. Uh, and the reverse implication amounts to a kind of sophicity question. Don't want to go too much into detail. Okay, so we can use some of this classical algebraic analysis of these problems to generate new interesting theorems in the Borel setting, and in fact, we can then feed that back into some graph limit machinery to get new interesting finitary theorems, or at least results that I couldn't find by Googling very easily. Not sure how new it is exactly. Okay, good. Let me end with a few problems that I think are interesting and that I think could involve some algebraic insight. So first, there are a couple of conjectures floating around about where exactly the complexity cutoff should be for these Borel CSPs. So I've conjectured, and I think Zoltan and Hansa Grebek have also conjectured that the Borel CSPs that are sigma 1, 2 complete should be exactly those structures, those attached to structures that don't have bounded width. So if you're not familiar, one way of saying that a structure has bounded width is that D has so-called WNU polymorphisms, weak near unanimity polymorphisms of all large enough arity. Okay, so weak near unanimity polymorphism says that uh, if we plug in x for all but one variable, it doesn't matter where we plug in that x, where we plug in that y, we should always get the same answer. Okay. And Zoltan, at least in talks, I'm not sure if he said this in print, but he's also conjectured that complexity should be characterized by having a non-trivial countable arity polymorphism. What he means by non-trivial is that it should be discontinuous, but also Borel. Okay. And various directions of these are known. For instance, it's known that if you don't have bounded width, then your sigma 1, 2 complete. Right? Zoltan and Hansa showed that systems of linear equations over finite field are sigma 1, 2 complete. And applying some of this simple definability machinery I've sketched gives you the complexity for bounded width problems. Sorry, non-bounded width problems. And a question that is really just algebraic is, are these two conjectures equivalent? So is it the case that D has bounded width if and only if it has a discontinuous countable arity Borel polymorphism? And I'll point out that one of these directions is also known. If you are bounded width, if you're not bounded width, then essentially all of your polymorphisms are affine, and for the same reason that there's no interesting definable additive function on the reals, if all of your polymorphisms are affine, then you don't have a discontinuous countable arity Borel polymorphism. Okay, so that's one like purely algebraic question. Can you take these WNU polymorphisms of large enough arity and somehow patch them together to get something that's Borel and countable arity and discontinuous? Um, and slightly more open-ended, um, are there algebraic characterizations of these simple interpretability and definability relations? Um, right, or narrowing down the question somewhat. Um, there's that lemma about understanding the relationship between HSP of an algebra and HFs of the algebra. So for what varieties V is having a non-trivial member of V in your HSP the same as having a non-trivial member in your HS? It's a purely algebraic question that I don't know what an answer might look like, but it would be interesting to descriptive set theorists. And then lastly, a question that probably involve both algebraic and uh, uh, descriptive set theoretic insights. So if we have so we have a characterization now of when the full Borel CSP is trivial, right? That's with one. But what about if we zoom in on special cases? So if there are any descriptive set theory experts in the audience, maybe one that shines would be the hyperfinite setting. Um, or, I suppose you wouldn't expect that for Borel, but for measurable. So maybe I should say here, instead of hyperfinite, the finite Borel asymptotic dimension setting. Okay. Um, good. So those are some questions I think are interesting. Hopefully you will all go and answer them for me. But thanks for hearing me out.